All right, suppose I hand you two little bars. They don't look like much, gray, a bit scuffed, no batteries, no strings, no tricks. I put one on the table, and then I hold the other one above it. I let go, and instead of falling down like every sensible thing since the beginning of time, it snaps sideways and sticks. Not gently either. It lunges, as if it knew. Now that should bother you. It really should, because if you think about it, nothing touched anything. No pushing, no pulling with a rope, no visible hand reaching out. Just empty space, and yet bam, motion, force, direction, purpose, almost. If you're not at least a little disturbed by that, you're not paying attention. Here's the paradox that always makes me smile, we say very confidently. Oh yes, magnetism. That's obvious. We give it a name, and somehow the naming feels like understanding. But if I stop you and say, no, don't tell me the word. Tell me how one piece of metal knows the other piece of metal is there. Then suddenly we get quiet. We start waving our hands. We draw invisible lines in the air. We say things like field and hope that's the end of it. But it isn't the end of it. It's the beginning of the mystery. When I was a kid, this is a true story. I had a little magnet, and I asked my father how it worked. He didn't give me a definition. He said, imagine the space around it is doing something. That was not very satisfying. I wanted gears. I wanted hooks. I wanted something bumping into something else. Space doing something sounded like cheating, because all of our everyday experience is built on the idea that to make something move, you have to touch it. You push a chair, it slides. You throw a ball, it flies. Even the wind, well, that's air molecules banging into things. There's always a middleman. Something hits something else. But with magnets, the middleman seems to have taken the day off. You can put a piece of paper between them. You can put wood, plastic, glass. You can even put your hand there, please be careful. And the magnet doesn't care. It reaches right through as if nothing is there. And yet, oddly enough, if you put the wrong kind of metal in between, like iron, suddenly the story changes completely. Now the magnet gets excited. It rearranges the iron. It pulls harder. It's selective, picky, as if it has preferences. Now what kind of force is tasty? Here's another little discomforting thought. Take two magnets and try to push them together the wrong way. You know what happens? They refuse. You push harder and they push back harder. You let go and zip, they fly apart. Where did that energy come from? You didn't wind anything up. You didn't compress a spring. And yet energy was stored there, invisibly, in the act of holding them together. In empty space. That's the part that should make your eyebrows go up, because empty space, as far as common sense is concerned, is nothing. It's where nothing happens. And magnetism is telling us, very politely but very firmly, that this idea is wrong. If you sprinkle little iron filings around a magnet, everyone's done this at least once, usually while making a mess, you see these beautiful curved patterns. People like to say, ah yes, those are the magnetic field lines. But notice something subtle. The filings don't show you the field. They show you what iron does in the presence of whatever it is that's there. You're not seeing the thing itself, you're seeing its effects. Like watching leaves swirl and claiming you've seen the wind. And here's the funny part, even after you've seen those patterns 100 times, even after you can predict them, draw them, calculate them, there's still this nagging question. What exactly is curving? What exactly is filling the space between the magnets? We're very good as humans at getting used to miracles. The first time you see a magnet lift a paperclip, it's magic. The 100th time, it's boring. But boring doesn't mean understood. It just means familiar. Imagine just for a moment that you lived in a world without magnetism. No compasses, no motors, no electric generators, no hard drives, no speakers, no MRI machines peeking inside your body. You wouldn't even have light as you know it, but let's not get ahead of ourselves. In that world, someone hands you a magnet and says, watch this. Your whole picture of how forces work would crack open. Because magnetism doesn't just pull and push. It organizes. It aligns. It creates patterns at a distance. It's as if space itself has instructions written into it, and the magnet is just reminding space what to do. And here's the really sneaky part. Gravity also acts at a distance. So does electricity. We lump them all together and say, well, forces can act through fields. But magnetism is special. It doesn't act on everything. It ignores most stuff completely, and then suddenly, with the right material or the right moving charge, it becomes bossy. Why? That question, why this and not that, is the one that keeps you awake if you take magnetism seriously. Not the equations, not the diagrams, the selectivity, the personality of the force. I once tried to explain magnetism to someone using tiny invisible arrows living in space, all pointing different ways, and the magnet just lines them up. The person nodded, satisfied. But afterward I felt uneasy, because I had just replaced one mystery with another. Why are there arrows in space at all? Who put them there? What are they made of? You see, if you're honest, magnetism forces you to confront something uncomfortable. The universe doesn't owe you a mechanical picture. Sometimes there just isn't a little machine underneath, clicking away where you can point and say, ah, that's it. Sometimes the best you can do is describe how nature behaves with exquisite accuracy, and then sit back and marvel at the fact that it behaves that way at all. And yet, despite all this mystery, you can play with magnets. You can feel them. You can build things with them. You can predict exactly how strong they'll pull, how far their influence reaches, how they'll twist and turn. The mystery doesn't stop the understanding, it lives alongside it. That's the delicious tension. On the one hand, magnetism is deeply weird, action without contact, structure without substance, energy stored in space. On the other hand, it's perfectly lawful, perfectly precise, and utterly reliable. Nature saying, you may not picture me the way you like, but I'll be consistent. So we're left standing there, holding two little gray bars, watching them leap together through nothing at all, and realizing that the emptiness between them isn't empty. It's busy, it's active, it's up to something. And once you accept that, once you let go of the idea that space is just a passive stage, then the door opens to a much stranger and much more interesting story. If you want, I'll keep going. Good. Then let's poke at this thing a little, the way you'd poke a strange animal with a stick, not to be cruel, but because curiosity is irresistible. Take a compass. A simple, cheap one, a needle on a pin. Nothing fancy, you put it on the table, and the needle points north. Everyone nods, of course it does. But stop right there. Why north? Who told it? There's no sign saying, this way. And more importantly, why does it point that way no matter where you are? You can spin the compass, shake it, insult it. It settles down and calmly insists on the same direction. Now here's a delightful experiment. Bring a magnet close to the compass. The needle swivels. Suddenly north has moved. You didn't move the earth. You didn't repaint the sky. You just brought a little piece of metal nearby, and the compass changed its mind. That should feel outrageous. It's as if truth itself became local. What's happening, of course, is that the compass needle is a magnet too. Two magnets chatting quietly through space. And this brings us to a very curious realization. Magnetism is not just something magnets do, it's something they are. You don't attach magnetism to iron the way you paint a wall. The magnet is the effect. Now imagine you could shrink yourself down, way down, until atoms are the size of beach balls. Inside the magnet, things are going on. Little atomic magnets, all lined up like soldiers who finally agreed on a marching direction. In an ordinary piece of iron, those soldiers are disorganized. Each one is magnetic, yes, but they're pointing every which way, canceling each other out like a badly run committee. When you magnetize the iron, you're not adding anything. You're persuading, you're getting agreement. That alone is charming. Magnetism is a kind of microscopic politics. But here's where it gets interesting. Even if you accept that atoms behave like tiny magnets, and that's already asking a lot, you still haven't answered the original question. How does one atom tell another atom which way to point? How does the influence get out of the magnet and into the space around it? We say, the magnetic field. And again, that sounds like an answer, but it's really a description. It's like saying, people move because of traffic. Well, yes, but what's the traffic made of? Let me try an analogy that's almost right, which is the best kind of analogy. Imagine you're standing in a field of tall grass. You can't see the wind, but you can see the grass bend. If the wind changes, the pattern changes. If there's a gust, you see it race across the field. The wind is real even though you never see it directly. Magnetism is like that, except stranger. Because the grass, isn't just sitting there waiting to be bent. The grass, the iron filings, the compass needles, the electrons in atoms are part of the phenomenon. They don't merely reveal the magnetic field, they participate in it. And unlike wind, which is made of air molecules you can bottle and weigh, the magnetic field doesn't seem to be made of anything at all. You can't scoop it up, you can't drain it away. You can only feel it by what it makes other things do. Now here's a playful thought. Suppose you had never heard of magnetism, but you were allowed to do experiments. You'd notice that when electric charges move, say electrons flowing in a wire, magnets suddenly appear. A current carrying wire deflects a compass. Wrap the wire into a coil and suddenly you've got a magnet you can turn on and off. No iron required. Just moving charge. That's a shock. Because now magnetism isn't just about special rocks or metals. It's about motion. Electricity in motion makes magnetism, and magnetism in turn pushes on moving charges. The force only shows up when something is already in motion. Standing still, nothing happens. Start moving and suddenly the universe has an opinion about your direction. This is one of my favorite quirks of nature. Magnetism is picky not only about materials but about motion. It's the ultimate conditional force. I'll act, it says, but only if you're already doing something. You can feel this in your hands if you play with magnets the right way. Try moving a magnet quickly past a copper pipe, not iron, just plain copper. The magnet slows down as if swimming through syrup. The pipe heats up slightly. Energy is being transferred. But copper isn't magnetic in the usual sense. So what's grabbing the magnet? What's happening is that the moving magnetic field stirs up tiny electric currents in the copper. Those currents create their own magnetic fields which push back. The magnet is fighting the consequences of its own motion, action, reaction, and a wonderful demonstration that magnetism and electricity are not separate actors, they're dance partners. At this point, you might be tempted to say, aha, so magnetism is really just electricity in disguise. And you wouldn't be wrong, but you wouldn't be completely right either, because now you have to explain electricity, and that opens another box of snakes. Still, there's something deeply satisfying here. Magnetism isn't a mysterious extra ingredient sprinkled onto the universe. It's woven into the behavior of charges in motion and space itself. It's not an add-on, it's a consequence. And yet, despite all this, if I ask you again, how does the magnet reach across space? You might still feel that itch. You've traded one mystery for a more elaborate one. Fields, charges, motion, fine. But what is actually happening in the space between? Here's where I like to slow down and enjoy the confusion. Because the urge to demand a picture, to insist on a mechanical story with little balls and springs is very strong, but nature is under no obligation to satisfy that urge. What it offers instead is consistency, rules that work, patterns that repeat. The magnetic field is not a thing you can hold. It's a set of instructions about how charged particles and magnetic materials will behave if they happen to be there. It's less like a substance and more like a promise, or a threat, depending on which way you're moving. Once you accept that, a lot of things start to feel less spooky. The space around a magnet isn't empty, it's prime, ready structured. And when something capable of responding enters that space, the structure reveals itself. That's a subtle shift in thinking. Space is no longer just where things happen, it's part of what happens. And if you're feeling a little uneasy about that, good. That discomfort is the sign you're getting closer to the truth. Because once you really digest this idea, once you let go of the need for contact and start trusting fields, then magnetism stops being an isolated curiosity and starts becoming a clue. A hint about how deeply interconnected motion, force, and space really are. And that hint leads somewhere surprising. Shall we keep pulling on the thread? All right, now we're far enough in that we can't pretend this is just a clever trick with metal anymore. We have to face the uncomfortable part, the part where magnetism stops being merely strange and starts being deeply counterintuitive. Let me tell you something that sounds wrong the first time you hear it, and still sounds wrong the 100th time, even when you know it's true. A magnetic force does no work on a moving electric charge. None. Zero. That should stop you cold. Because earlier we said magnetism can slow a magnet falling through a copper pipe. It can bend the path of electrons. It can twist motors, generate electricity, heat up metal. All of that looks like work. Energy is moving around. Things are changing. And yet, if you zoom in on a single charged particle, a lonely electron flying through a magnetic field, the magnetic force on it is always sideways to its motion, always at right angles, pushed sideways, not forward or backward. That means the force can change the direction of motion, but not the speed. The electron curves, spirals, loops around, but it never gains or loses kinetic energy from the magnetic field itself. It's like running in a perfect circle while someone keeps shoving you sideways. You change where you're going, but not how fast. Now pause and savor that, because it's extraordinary. A force that can completely rearrange motion without ever doing work. A kind of cosmic steering wheel with no gas pedal. This is not how we're used to thinking about forces. Gravity pulls you down faster and faster. Springs push back and store energy. Friction robs you blind. Magnetism just nudges, relentlessly, precisely, sideways. And the equation that describes this, simple, compact, and loaded with meaning, says that the magnetic force depends on how fast the charge is moving and which way crossed with the magnetic field. Crossed, not added. Direction matters. Orientation matters. Turn around, and the force flips. Slow down, and it weakens. Stop, and it vanishes completely. This is why magnetism feels so slippery. You can't pin it down unless something is already in motion. It refuses to act on stillness. Now let's make it even stranger. Suppose you and I are floating in space, far from everything, watching a charged particle drift by. In your frame of reference, the particle is moving, and you see a magnetic force. In another frame, one moving alongside the particle, the charge is at rest, no motion, no magnetic force. So which is it? Is there a force, or isn't there? The answer, delightfully, is yes. What changes between frames is not just motion, but the split between electricity and magnetism. What looks like a magnetic force in one frame can look like an electric force in another. They're not separate entities with independent existences. They're different aspects of the same thing, revealed depending on how you're moving. This is one of those moments where the universe quietly laughs at our categories. Electricity and magnetism are not two forces glued together. They are one phenomenon stretched across space and time. Motion mixes them. Change your perspective, and electric fields turn into magnetic fields the way shadows turn into shapes when you move the light. This is not philosophy. This is measurable, predictable. Engineers use it every day without losing sleep over it. But conceptually, it's wild, because now magnetism is telling us something profound. Forces are not absolute. They depend on how you're moving through the world. Nature doesn't come labeled with neat compartments. We draw the boundaries because it helps us think, but the universe doesn't respect them. And then there's the quantum twist. Inside atoms, electrons don't orbit like little planets, despite the pictures we draw. They behave like smeared-out waves with intrinsic properties. One of those properties is something we call spin, which is a terrible name because it's not literally spinning, but never mind, we're stuck with it. What matters is this: spin gives electrons a built-in magnetism. Every electron is a tiny magnet, not because it's moving in a loop the way we might imagine, but because that's how the rules of the universe are written. No gears, no classical picture, just this is how it is. So when you hold a magnet in your hand, its strength comes not from vast numbers of electrons orbiting wildly, but from the quiet alignment of these intrinsic magnetic moments. A subtle quantum agreement, billions upon billions of tiny yeses pointing the same way. An alignment, it turns out, is everything. Heat a magnet enough and it loses its magnetism. Why? Because thermal motion shakes the alignment apart. The electrons don't lose their magnetism, they just stop cooperating. Cool it down, and order can return. Magnetism is not destroyed, it's scrambled. This should sound familiar, because it's the same story everywhere in physics. Order versus disorder. Patterns emerging from chaos. Collective behavior creating something that no single piece fully explains. And through all of this, through electrons and fields and frames of reference, there's a deeper truth humming underneath. Magnetism is not a force acting through space. It is space behaving differently when charges move. That's a subtle but crucial shift. The field is not something sitting in space like fog. It's a condition of space. a rule about how motion and charge interact, which brings us back to those iron filings on the table. They're not tracing out invisible wires. They're finding the directions where alignment is easiest. They're settling into the geometry that space itself prefers in the presence of a magnet. Geometry. That word should make you suspicious in a good way, because once geometry enters the story, once forces start looking like consequences of structure rather than pushes and pulls, you're very close to something profound. You're close to the idea that what we experience as force might be the universe's way of enforcing consistency. Magnetism doesn't shove electrons around because it wants to. It deflects them because that's the only way motion, charge, and space can coexist without contradiction. At this point, the mystery hasn't gone away, but it has changed character. It's no longer, how does the magnet reach across space? It's why is space built this way at all? And that question doesn't just belong to magnetism. It belongs to everything. Once you start asking it, you realize magnetism isn't an odd side story in physics. It's a window, a crack in the wall that lets you glimpse how deeply strange and how deeply coherent the universe really is. And if you step back just a little farther, that coherence starts to look almost philosophical, which is where this is headed next, whether we like it or not.